Today we're going to move from absolute value functions to quadratic functions. And before focusing solely on the quadratic functions, we're going to compare the vertex term of a quadratic function to the absolute value function, so we can see some similarities and we can see some differences. Now, the table for the absolute value function should be familiar by now. The table for a quadratic function, we're going to plug in our x values into the function up here. -2 squared is 4. -1 squared is 1, 0, 1, and 4. So you may notice some similarities. Firstly, we see that there is some symmetry between them. We have the same thing over here with the quadratic function. Now, what you will also see about the table from the quadratic function is that if we take the difference, let me erase this. So the difference here, 4 minus 1 is 3, 1 minus 0 is 1, 0 minus 1 is -1, 1 minus 4 is -3. So it's not the same value like it is over here. Okay, 2 minus 1 is 1, 1 minus 0 is 1, 0 minus 1 is -1, 2 minus 1, 1 minus 2 is -1 as well. So we see it's 1, 1, -1, -1. It's the same number, just different signs. Whereas the quadratic function, it went 3, 1, -1, -3. But if you took the second difference, and that's subtracting these numbers, 3 minus 1 is 2, 1 minus -1 is +2, and -1 minus -3 is also 2. This is called the second difference. Second difference. And the reason why it's called second difference is we took the y values, we subtracted them once, and this where this 3, 1, -1, -3 came from. And then we subtracted those values and got 2, 2, and 2. That is a second difference. That is how you can tell that a table is a quadratic function. So we will be using that frequently. Let's look at the graph. Absolute value again. We know how to graph that. Graphing the points from the table above. The quadratic function, I'm going to graph those points. So here are the points for the quadratic function. And you'll notice that the quadratic function grows a lot faster. It goes up a lot quicker than the absolute value function does. So the shape of the absolute value function, that was a V shape. The shape of the quadratic function, you can call it a U shape, but the technical term is called a parabola. And people will mix this up a lot. They'll be given a quadratic function like that and say, oh, that's a parabola. The graph is called a parabola. This is not a parabola function. It's a quadratic function, and the graph is called a parabola. The vertex, both of these have a vertex, 0, 0. And for the parabola over here, it had a point at 0, 0 as well. So they both have a vertex, and in this case, it is the same value. Domain and range. We know for the absolute value function, the domain was -infinity, infinity. And in this instance, the range, the smallest y value is 0. and we go all the way up to infinity. The exact same happens with our quadratic function over here. The graph has the smallest y values right here, and our y values are going up, so the range is the same, and the domain is also the same. End behavior. Look at both of these graphs, the ends go in the same direction. For the left side, in the absolute value function, the y values are increasing. The same thing is happening with my quadratic function. The right side is going up, the right side is going up. It doesn't matter if the ends are going up faster, it just matters that they are going up towards infinity. So both ends here are going towards infinity. So there are a lot of similarities here. There's the vertex is the same, domain's the same, range is figured out the same way, same thing with end behavior. The big difference is that we have the term called second difference here. We don't have that in an absolute value function. All right, so let's look down here at an actual example of an absolute value in a vertex form of a quadratic, and we're going to graph both of these and we're going to compare them to the parent function. And again, you're going to see a lot of similarities between these two graphs. Right, so we know that there is a reflection over x-axis. We know there's a vertical stretch because our a value is 3. And our translation we know is right 5 and up 4. The same thing applies for the quadratic over here, since this is in vertex form. We do have a reflection over the x-axis. We do have a vertical stretch, and we also have a translation of right 5 and up 4. So we'll graph the absolute value function first. 1, 2, 3, 4, 5, and up 4. And our slope here is -3. So we'll go down 3. 1, 2, 3 over 1. And our graph looks like that. And again, this was a V shape. Our vertex was at 5, 4. And for the table, we can put the vertex in the middle. And then the x values are going to go down by 1 and up by 1. And we can see from our graph that the y values change by, are going down by 3. And you see that these y values match, and these y values match. Domain, -infinity, infinity. And then the range, the biggest y value is 4, and the y values go all the way down. So the range will be -infinity, 4. And since both ends go down, the end behavior is -infinity. Now, when I graph quadratics, I like to start with the table and vertex first. We know the vertex is the same as it was for the absolute value function, and we're going to put that in the center. And our x values are going to go down by 1 and up by 1. Then we're going to plug in our x values into our equation up here. And since we know that this is going to be symmetrical, we only need to plug in 2 of the numbers. So we can plug in 4 and we get 1. And then we can plug in 3 and we get -8. So 1 and -8. That means that this y value here must be 1 and this one must be -8 as well. And again, if we take the difference in these y values, we get -8 minus 1 is -9. 1 minus 4 is -3. 4 minus 1 is 3. And 1 minus -8 is 9. You don't have to calculate the first and second difference unless I've asked you to or you need to in order to solve the problem. I'm just showing you so you guys get used to what it looks like. 9 minus -3 is -6. -3 minus 3 is -6. And 3 minus 9 is -6 as well. So this second difference here is -6. Okay, so then let's go ahead and plot these points. We have 4, 1, 6, 1, and then -8. And then -8 here as well. So this is still a parabola. And the vertex is still 5, 4. And just like what we had up here, the domain, range, and end behavior are going to be the exact same as the absolute value function that we just got done writing. So domain, the range, and then the end behavior is the same. And that should make sense. If you look at our graph, the biggest y value we have is right here at 4. And the graph goes down, and the y values go all the way down to -infinity. And both ends are going down, so that's why the y values, or g of x here, approaches -infinity. Okay, now let's look at the summary. The effect of A, it's a little bit different on both on absolute value and the vertex form of the quadratic. It does A does tell you if you have a shrink or stretch, does tell you if you have a reflection. In the absolute value function, though, it is also the slope of the two lines, or the lines of the V, whereas the vertex form, it still is a shrink or stretch. We still have a reflection, and the A value is also half the second difference, and I'm going to show you that on the previous example. So here our second difference was -6. Look at our A value. It was -3. Up here, our second difference was 2. Our A value is at invisible 1. So your second difference, your A value is going to be half of your second difference. The effect of H, the same effect. It's your horizontal shift And again, it is the opposite of what you see. K is your vertical shift. And that is exactly what you see. Your vertex for both of these, it was h comma k. Your min or max value, if a is positive, that means you have a minimum value at y equals k. And if a is negative, which means their graph is opening down, you have a max at y equals k. Look here, our graphs are opening down, and the biggest y value was the y coordinate of our vertex. Domain. The domain for both of these is -infinity, infinity. Your range. Well, if a is positive, the function opens upwards. So the smallest y value will be our k value of the vertex and go up towards infinity. And if a is negative, meaning where our function opens downwards, that means the smallest value is going to be -infinity, and the k value of our vertex is the largest value. Again, up here, look at our a value is negative here. Our range went from -infinity to the y coordinate of the vertex. Here, even though this was just the normal parent function, it's opened upwards. Our range was the y value of the vertex, comma, positive infinity. And then the last thing, end behavior. If a is positive, both ends go up. And if a is negative, both ends go down to -infinity. So this is a good reference sheet to have to really determine the difference between graphing absolute value equations and vertex form of quadratics. On the next page, we're going to graph these examples here and list the desired information. So 1/2 x squared. We have no reflection. We have a vertical shrink. Translation, we have no translation. There is no plus or minus anything, so none. The domain, range, vertex, min, and max. I sometimes like to graph, or at least have the table done, and then come back and do these. So let's make a table here. And our vertex will go in the middle. Since we don't have a translation, our vertex is 0, 0. And our x values are going to go down by 1 and up by 1. So if I plug in 1, 1 squared is 1 times 1/2 is 1/2 or 0.5. It doesn't matter which what you use. 2 squared is 4 times 1/2 is 2. And then we know that these should match and these should match. We're not asked to find the second difference, so I'm going to save that for later. So let's plot these points. So my graph looks like this. The domain for every single quadratic equation or quadratic function is -infinity, infinity, always. Our range, our smallest y value is 0, and the y values go all the way up to infinity. Min or max, we have a minimum value at y equals 0. End behavior, both ends are going up towards positive infinity. Number 2 over here, we do have a reflection because a is negative. Shrink or stretch, we have a vertical stretch. And translation, again, we have no translation. Our table over here. And our vertex, as we have no translation, is still 0, 0. Now when we plug in our x values, if we plug in -1, -1 squared is 1 times -4 is -4. -2 squared is +4 times -4 is -16. And then these y values should match. So I know that we're going to go off the grid a little bit with our y values, and that's okay. 0, 0. And 16 is going to be way down here, but I don't want to get it on the other problem. So we'll make it work like that. The domain is still -infinity, infinity. The range, since this is open downward, the y values go all the way down to -infinity, and the largest y value is that y coordinate of the vertex, which is 0. Your vertex is 0, 0. We have a maximum this time, maximum at y equals 0, and both ends are going down to -infinity. Number 3 over here, you may say, well, that's not in vertex form. Well, this one is in vertex form. We just don't have an h value, and that's okay. So we have no reflection. Our a value is positive. Our a values is 1, so we have no shrink or stretch. Our translation is just down 5. Right, so then let's make our table here. Whoops. And he says we're not shifted left or right any. Our x value of the vertex is still 0. And we are down 5, so let me fix that. There we go, -5. And then for the rest of the table, and then we can plug in our x values. 1 squared is 1, -5 is -4. 2 squared is 4, -5 is -1. And again, these should match. So you only really need to do 2 additional points and then just reflect them. And then when we graph them, there's my vertex. And here are my points. So our graph looks like that. Domain is always like that. Our range. We are opened upward, so the smallest y value is the y coordinate of our vertex, and the y value goes all the way up to positive infinity. This means we have a minimum value at y equals -5, and since we are opened upwards, this u opens up, the end behavior goes to infinity on both sides. Okay. So what I want you to do is I want you to pause the video, try number 4, and once you are done with number 4, unpause it and check your answers. All right, so here is the answer for number 4 with all the information provided. So take a minute to check your work. And I know this graph also went off the grid a bit, and that's okay. As long as you got all this information down, you'll be in good shape. So I know that there was a lot of information here, but hopefully by comparing it to the absolute value functions that you've just done, I know that this is a lot of information, but hopefully comparing it to graphing absolute value functions, graphing these quadratic functions in vertex form is a little bit easier because a lot of the same things apply. There's only a couple differences between the two. So thanks for watching the video. Make sure to like it and subscribe.